Hello everyone, this is Mrs. Dipti Kulkarni, lecturer, Department of Physics, KLS Kokte PU College, Belgavi. In continuation with my earlier video on electrostatic potential and capacitance. In this video I am going to discuss few more concepts from the same chapter. Let us begin with superposition principle of electric potentials. Already we discussed superposition principle in the first chapter. Okay, the same superposition principle we are going to study or we are going to apply for the electric potentials. What is electric potential? We discussed already in the previous video. Okay, so now here derivation based on the superposition principle, okay, of electric potential. To find electric potential due to group of n point charges, means in the system, suppose if we consider n number of point charges, then what is the total potential, electric potential? Statement: the electric potential at a given point due to a group of charges is the algebraic sum of the all potentials due to all the charges. Okay, this is what? This is the statement of superposition principle. So group of means in the system many number of charges. Suppose if we consider n number, n means many number, okay, many charges. Okay, now so if we consider this is a system or a group, in this group how many charges I considered? Q1, Q2, Q3, Q4. Similarly, I can consider n number of charges. Okay, so I can draw like this, n number of charges. So I may call it as Q5 or Qn. Okay, now if we join the lines from this Q1 to P, Q2 to P and Q3, Q4 to P. P is a point if we consider the point, and these are imaginary. Okay, whatever we have assumed here in this diagram, that is imaginary. Okay, from the point P to the Q1, charge Q1, the distance is R1. And whenever we say that consider a point means there is a charge always, but the magnitude is negligible. Okay, maybe it is 1 coulomb. So we have to mention only a point here, not a charge value, or we should not mention the charge Q or some other notation. So P means it is understood that very negligible charge is present here, and the distance from this Q1 to P is R1. Similarly, the distance from Q2 to P is R2, R3, R4. Okay, now let Q1, Q2, Q3 so on up to Qn be the point charges placed at distances R1, R2, R3 up to Rn respectively from a point P. Okay, I hope you understood the diagram. Okay, now potential at P due to the charge Q1, V1 is equal to 1 by 4 pi epsilon naught Q1 divided by R1. What is electric potential formula, general expression? We already discussed general expression for the electric potential in the last video. What is that? Electric potential is denoted by V, and V is equal to 1 by 4 pi epsilon naught Q divided by R. So this is the general expression for the electric potential. Now suppose if we want to study the potential at P due to what? Due to the charge Q1. Means if we want to study this charge, okay, at this point due to Q1, then what is the formula for electric potential in that case? that is V1 is equal to 1 by 4 pi epsilon naught Q1 divided by R1. Similarly, electric potential at P due to the charge Q2, this Q2, what I have to write? V2 is equal to 1 by 4 pi epsilon naught Q2 divided by R2. So here it is. V2 is equal to 1 by 4 pi epsilon naught Q2 by R2. Okay. Similarly, so we can write for Q3, Q4, Q5, so on up to Qn. Potential at P due to the charge Qn, that is Vn is equal to 1 by 4 pi epsilon naught Qn divided by Rn. From superposition principle, the total electric potential. So from the superposition principle, just now what we studied here, from this principle we can take algebraic sum of all the potentials. Algebraic sum of potentials means what? We can add all the potentials. Okay. So total potential V is equal to V1 plus V2 plus so on up to Vn. So we know what is V1, V2, V3 or Vn. Okay. Substitute the values, these values in the given or in this equation. Then V is equal to 1 by 4 pi epsilon naught Q1 divided by R1 plus 1 by epsilon naught Q2 by R2 so on up to where Qn divided by Rn. And here 1 by 4 pi epsilon naught is common, that is constant value. So I will consider this common factor, okay, here outside the bracket. Inside the bracket, what I have to write in this step? Q1 divided by R1, Q2 by R2 and similarly Q3 by R3 so on up to where Qn divided by Rn. So this is what? Total electric potential. After this step, so we can write in this way also. Okay. Now you just carefully see, can we simplify this one? Is it possible? Yes, of course. How? V as it is, 1 by 4 pi epsilon naught as it is. We are not varying these two here. What is varying? So you just carefully see 1, 2, 3. Charge numbers are varying. Similarly, distance numbers are varying here. 1, 2, 3 up to n number. And here also 1, 2, 3 up to n, Qn. Okay. So 1 by 4 pi epsilon naught summation of Qi divided by Ri, where I is integer here and we have to consider I from 1 to n number. Okay. So this is the final expression for the electric potential if we study the superposition principle. Okay. For how many charges? For n number of charges in the system, then only this is applicable. Okay. I hope you understood all the steps properly. Now next concept, equipotential surface with example. Equipotential surface means what? It is the surface having the same electric potential at every point. The sentence is very simple. The surface having the same electric potential at every point. Suppose if we consider this is an imaginary surface, if we measure the electric potential here, so everywhere it is same. Okay. So the meaning of this sentence is what? Electric potential at every point it is same. So this is one example. The surface of a charged body of any shapes. Okay. So I had taken a few more examples here. Equipotential surface for uniform electric field. So these are these arrows. Okay. Lines, these shows the electric field lines. These are electric field lines. Suppose if we consider this type of a diagram, there also equipotential surface is equipotential surface we can study in the uniform electric field also, or the surface in this surface the potential, electric potential is the same. At every point electric potential is same. Suppose if we consider this type of surface. Okay. Next, suppose if we consider the dipole. Okay. The charge surrounded area, this surface, and this charge surrounded area surface. Here also we can study the electric potential. So this is also one more example for equipotential surface for a dipole. This is for dipole. Dipole means what? Positive, negative charge. If both poles are present, then we say that it is a dipole. This is one more example. Equipotential surface for a pair of equal positive charges. Suppose if we consider two similar charges, okay, then this imaginary surface, equipotential surface. We can study the electric potential for this type of pattern also. Okay. So these are the few examples which shows the equipotential surface. Now the properties. Let us understand one by one. Properties of equipotential surfaces. Number 1, no two equipotential surfaces intersect. Okay. No two equipotential surfaces intersect. They never intersect with each other. This is first one. Second one, work done is 0 in moving a test charge over an equipotential surface. Work done is 0 in moving a test charge over an equipotential surface. Third one, the direction of electric field is always normal to the equipotential surface. The direction of electric field is always normal. Normal means what? It is perpendicular to the equipotential surface. Electric field is always normal means this is always perpendicular to the equipotential surface. Fourth one, equipotential surfaces are closer in the region of a strong electric field. Equipotential surfaces are closer in the region of strong electric field. Okay. They are farther in the region of weak electric field. If electric field is strong, then equipotential surfaces are closer. If the electric field is weak, then the equipotential surfaces are farther. The distance is more. Okay. So these are the few properties of what? Equipotential surfaces. Now, based on today's or from this video, I am going to discuss few questions which are very simple. So this is your quiz time. Okay. Now I just prepared few simple questions based on the previous slides. Okay. Let us begin one by one. First one, dash two equipotential surfaces intersect. Second one, work done is dash in moving a test charge over an equipotential surface. Third one, expression for electric potential. So, pause the video, once again read the questions and cross check your answer. First answer, no. No two equipotential surfaces intersect. So this already we discussed the property. Okay. Properties of what? Equipotential surface. Second one, 0. Work done is 0 in moving test charge over an equipotential surface. Third one, general expression for equipotential surface or electric potential, V is equal to what? 1 by 4 pi epsilon naught Q by R. Electric potential general expression is what? V is equal to 1 by 4 pi epsilon naught Q by R. I hope you understood the concepts properly. If you want further questions and answers from the second chapter, please go through the link given below. Thank you.